Okay, welcome everybody to this second session of our SPDE seminar. Today we have Kevin Young from Stanford University. Kevin is a PhD student at Stanford University under the supervision of Amir Dembo, and we are very happy to have you here today. So Kevin will speak about the KPZ equation from some long-range particle systems.
Thank you for the introduction and also the invitation to speak. I don't know exactly if there's a protocol for asking questions or anything, but feel free to interrupt me whenever. And you can also type in the chat, but I can't promise that I'll see it in real time. So as Karsten mentioned, I'll be talking about the Kardar-Parisi-Zhang stochastic PDE and its role as a scaling limit or continuum model for interfaces associated to long-range particle systems. So given that this is a stochastic PDE seminar, I'll start off by introducing the relevant SPDE, which is this KPZ equation written at the top of the slide here. So at face value, this KPZ equation is some linear parabolic stochastic PDE to start with this Gaussian space-time white noise, which you can think of as uncorrelated Gaussian random variables at every space-time point, with an additional gradient nonlinearity. So throughout this talk, anything that's in pink doesn't necessarily mean something related to this nonlinearity. It's just something that I want to draw more attention to. So if you think about this KPZ equation really as a perturbation of the linearization, you'll run into trouble. In particular, if you try to approach this equation by studying it through classical PDE theory, you'll get something that's ill-posed. And this is precisely due to the lack of spatial regularity of the space-time white noise. So to overcome this obstruction, I'll adopt what's known as the Cole-Hopf solution theory, which you can take from this paper by Bertini and Giacomini, which I'll reference throughout the talk occasionally. And the point of this Cole-Hopf solution theory is to simply define the solution to this KPZ equation through taking the logarithm up to a sign of the solution to this stochastic heat equation down here, which is linear and has a multiplicative noise instead of an additive noise. So there are two upshots. The first of which is that this stochastic PDE down here with the multiplicative noise, if you reinterpret it in the mild formulation through some heat kernel expansion, it turns out to be well posed with probability 1 in a space of space-time continuous functions, which you can establish through the Ito calculus. And on top of that, if you start off with positive initial data, for example, a comparison principle of Mueller from almost 30 years ago will guarantee that the solution remains positive with probability 1, which allows us to actually take this logarithm. So in that sense, this equation is well posed. And in terms of where this solution theory comes from, if you formally apply the Ito formula with respect to the space-time white noise through this exponential transform, you'll go between the two equations. Though again, this procedure is not rigorous and it's ill-posed because of the lack of spatial regularity in the white noise. So that's just a brief stochastic analytic introduction to this KPZ equation. In terms of where this equation comes from, or its physical or probabilistic content, it was derived through physical heuristics, which I'll describe shortly to some extent, by Kardar-Parisi and Zhang 10 years before this Bertini-Giacomini article. And it was obtained or derived to be a universal model for dynamical interface fluctuations, satisfying three sort of key features. The first of these features is a local smoothing mechanism for the interface. So if you imagine some sort of interface, it's sort of at local scale smoothing itself out. And this corresponds to the Laplacian on the right-hand side of the equation. And the space-time white noise in the equation corresponds to some sort of uncorrelated or independent random growth mechanism in the interface. And then the last of these features, which is the most important concerning the KPZ equation itself, is a slope-dependent growth mechanism in the interface, which corresponds to this nonlinearity in pink here. And to give you just sort of a brief taste of the universality that was of interest in this Kardar-Parisi-Zhang paper. If I take any nonlinearity of the slope, so any sort of slope-dependent growth mechanism, and I Taylor expand this thing formally, well, the first two terms on the right-hand side of the Taylor expansion can be sort of eliminated through a linear change of coordinates, which is a standard thing to do in PDE theory. And then the first non-trivial term that you see is this quadratic nonlinearity, and that's where this thing comes from. So the content of this talk is primarily going to be motivated by this question of, to what extent is the KPZ equation a universal model for dynamical interface fluctuations? So just to provide an introduction to this problem, you can look at interfaces associated to semi-linear stochastic PDEs, which is basically the situation from the previous slide of a generic nonlinearity of this derivative. And there are a couple of papers by Heyer and Costel and Heyer and Su, in which they basically make the previous calculation with Taylor expansion rigorous through something called the theory of regularity structures. But it turns out that there's some additional renormalization that needs to be considered in that Taylor expansion calculation. And related to this is another work of Gubinelli and Perkovsky, which I won't explain in too much detail, but it is along these same lines. And then there's another class of models, which are statistical mechanical models given by directed polymers in random environments, in which case it's not sort of an interface that you're looking at exactly, it's the free energy. And the paper here that I'm going to be referencing just for now is this paper by Alberts, Kahn, and Costel. The main class of models in the context of the universality problem here that I'm going to be interested in is interfaces associated to interacting particle systems. So on this slide, everything that's boxed is just going to be everything that's more relevant or directly relevant to the content of this talk. So at least in my head, I like to think of sort of among interacting particle systems, sort of three classes or three groups of interacting particle systems. The first group is a class of systems which exhibit some sort of algebraic structure or integrability. And there are many more papers beyond the three that I've listed just here. But the one that I'm going to be sort of focusing on more is this paper of Bertini-Giacomini in this talk. And then beyond particle systems with this exact integrable structure, you can consider particle systems which have some sort of algebraic structure, in a sense that I'll define later in the talk, but not quite. You have some maybe error terms in addition to this algebraic structure. And this paper of Amir Dembo and Li Cheng-Sai from several years ago is sort of the thing that I'm thinking about. And I'll explain the content of that paper later in the talk as well. And then you can try to take sort of an orthogonal approach, but it's all, again, part of the same story, which is this theory of energy solutions. And the upshot to this sort of approach to studying interacting particle systems in the context of this universality problem is the fact that the particle system doesn't need to exhibit any sort of algebraic structure or integrability. So in that case, in that sense, it's much more robust, but it does suffer from, or it does require a very strong assumption, and that the interacting particle system you work with has to have a fairly explicit and reasonably well-behaved invariant measure, and the particle system needs to start at that invariant measure. So these are just sort of three types of models that I'm thinking about. And now I'll give you an example of one of these particle systems, which is the asymmetric simple exclusion process, which is the particle system considered in this Bertini-Giacomini paper. So this particle system is fairly easy to describe. There's a schematic here, but basically what's happening is I have a system of particles on the integer lattice subject to two constraints. The first of which is oh, am I cutting out or?
No, you're fine.
Okay. So if you, so ASEP, which is the abbreviation, is a system of particles on the integer lattice subject to two constraints. The first of which is that every site has at most one particle. And the second constraint is that every particle just performs an independent simple random walk, but subject to not being able to jump onto already occupied sites, which is sort of the exclusion principle in this particle system. And then the simple random walk that the particles are performing have a step distribution, which is basically symmetric, except you have an asymmetry on the order of n to the -1/2. And here n is going to be some scaling parameter going to infinity that gives us our scaling limit. So that's ASEP. And associated to ASEP is some dynamical interface, which is, again, sort of fairly straightforward to describe. So given any particle configuration, as the schematic is supposed to sort of illustrate, you associate an interface, which is just a simple random walk path that goes up at a site X if there's a particle there, and otherwise it goes down. And because ASEP can be thought of, or really is, an evolution on particle configurations, you obtain a dynamic on the associated interface, and this is the thing that's supposed to give us the KPZ equation in the scaling limit. So more precisely, if I renormalize the interface, first by applying parabolic scaling in spacetime and then scaling the overall height by n to the -1/2, and then I include this additional renormalization, which comes from the fact that there's an asymmetry in the particle of random walk, the theorem of, or one theorem in Bertini-Giacomini's article is that if initially under the scaling, the height function or the interface approximates some sufficiently Holder continuous function, then the solution or this renormalized interface in spacetime will converge to the solution of the KPZ equation. So this is just to be this sort of topology that I've given here about local Holder continuous convergence or local uniform convergence is just to make sure that I'm not sort of hiding anything or lying to you in any sort of way. But this is the theorem of Bertini-Giacomini. And on top of this, on top of the convergence itself, this provides some sort of physical justification for the Kohlhoff solution theory that I described before.
Kevin, I have some minor questions about the coefficient, the constants.
Oh,
so
yeah.
First, where does this T over 24 come from?
Oh, so I guess one way to answer your question is that if I don't include the 1 over 24 times T,
right. I mean, it seems to me that Bertini-Giacomini wouldn't have seen this T over 24. It won't. It's not in the paper.
Well, it's a quantity that isn't depending on n, so you know one doesn't necessarily need to include it. But if you want, I guess, to get to the right version of stochastic heat equation, then you need it, right? It comes from a sort of Taylor expansion of terms, right? There's, I don't know, a 1/6 and a 1/8 whose difference gives you a 1 over 24 or something like that.
But I thought, you know, in Bertini-Giacomini, because you're working with height function, the thing without 1 over 24 would go to SHE. It's only when you compare SHE with Tracy-Wheaton you have this T over 24.
So
if
what I can tell you in response to your question, Li Chang, is that actually, I mean, you can see this 1 over 24 times T from the expansion that you performed within your demo in your paper, actually. So it is part of the Taylor expansion calculation that Ivan was talking about.
Okay, that must be wrong. So there's, I'm not sure if I follow your sign, that your Hofkohl has a negative sign, but I thought that should be positive if your KPZ equation has a positive quadratic term. It also relates to your initial data, whether it's negative of a heat kernel or it's positive of heat kernel.
So, okay, so I guess, yeah, thank you for the subtlety in the sign. So I guess really what I should be considering is instead an asymmetry in the other direction.
Right. Okay.
Yeah. Thank you for that.
Thank you.
Are there any other questions before I go on? Okay. So in terms of this Bertini-Giacomini theorem, literally what's done, because they adopt the Kohl-Hopf solution theory in that paper, is they exponentiate the height function in this fashion, and they show that as n goes to infinity, you recover the solution to the stochastic heat equation. And in some sense, this is what you have to do with the Kohl-Hopf solution theory, because the stochastic heat equation is the only thing that we know how to make direct sense of from this perspective. And concerning the initial data, you can actually extend the result, not just the Holder continuous initial conditions, but singular initial conditions, including the narrow wedge initial data. This paper of Amir Cohen-Questel, where the year, I think here is the archive preprint year, not the publication year. And literally, the narrow wedge initial condition, or formally, is this singular object in which I try to take the logarithm of a delta function, but you can think of it as the fundamental solution of the stochastic heat equation after I exponentiate. And just as a sort of brief remark, the reason why you want to consider this initial condition is because of its important connection to random matrix, which I won't sort of talk about in too much detail, but it's there. Okay. So that was a result for ASEP, which is a model that has an algebraic integrable structure in a fashion, again, I'll define in the talk. But the motivating question for this talk is this universality problem for the KPZ equation. So I want to consider models that don't have this exact integrable structure. And one family, or the family I'm going to consider, are these long-range variations on ASEP, which are simple to define. It's the same thing as ASEP, except the particles can now perform random walks of arbitrary jump length. The real key feature here is that the asymmetry is on a scale of n to the -1/2, and that the step distribution of the particle random walks has enough moments, for example. So technically, it'll be convenient if you just assume that all moments of the coefficients or the step distribution for the particle random walk are uniformly bounded in the scaling parameter n, though you can certainly relax this condition to just some moments. And there's a more interesting condition that I'm going to talk about and assume, which is that the asymmetry coefficients in the particle random walk satisfy this system of linear equations, where here lambda is a function of the asymmetry coefficients and the symmetry coefficients. And there's sort of one objection you can raise to this, being that how do you know that a solution to the system of equations actually exists? So there's a magical feature to the system of linear equations if you forget this big O error term for now, in that if I start off with any non-zero lambda of interest, or positive lambda if you want to specialize to that, and then I just define asymmetry coefficients according to the system of linear equations without the big O term, and then I compute the corresponding lambda associated to those asymmetry coefficients, I'll get back the same lambda that I started with. So this seems to be, I think, the key feature of this system of linear equations. And in particular, if you apply sort of the analysis that I'm going to talk about later in this talk with that magical feature, this assumption is actually entirely removable if you start the equation at the invariant measure, or start the system.
Kevin, does this mean that so you choose your alphas, and then for any choice of alphas, there's a one parameter family of these?
Yes.
And that's, if you want to satisfy the magical assumption, that's it, right?
Yes.
One parameter family.
Exactly.
And then you're saying that if you, so this is for general initial data, but if you are willing to start in an invariant measure, then it will be totally general. You don't need to.
Yes. Exactly.
Okay. How does this assumption, in Li Cheng and Amir's work, there were some assumptions, they were dealing with shorter range, but still non-nearest neighbor. Does this assumption reduce to theirs in some way, or is this?
Yes, so it's exactly the same assumption. It turns out that the error term in their paper is n to the -1. The analysis I'll describe in this talk, combined with this magical feature I described, allows us to sort of relax the error term to n to the -1/2, it turns out. But sort of, if you ignore the big O term, it's exactly the assumption that was in Amir and Li Cheng's work.
And how should we think of the big O, because if you fix the alphas and then you choose the lambda, you're saying you don't actually have a big O term.
Yes.
So in reality, you're allowed to perturb the gammas by a little bit, right?
Yes. So I can tell you that this error term sort of wasn't on my mind when I was working on this problem, because I think the long range jumps feature was more interesting first. It just turns out that to handle certain quantities that arise from longer range jumps in the model, you can also use that strategy to sort of relax the constraint on this error. Okay. Does that answer your question?
Yeah.
Thank you.
But I think there was one question that Ivan asked about the jumping range. In the paper with Samir, we were only able to do up to 3, and now you allow general.
Yes. Okay. Thank you for the questions. The result for these long-range variations on ASEP is that if I renormalize the interface in basically the same fashion, where here nu n is now a quantity that depends explicitly on the coefficients of my model, and it's of the same scale of order n, the first result is that the theorem of Bertini-Giacomini is still true, except the KPZ equation you get might have different coefficients than the one that I gave in the first slide. And again, those coefficients in the limiting KPZ equation are also explicit in terms of the coefficients in my particle random walk model.
And you've checked the KPZ scaling theory is respected by the coefficients?
Yes.
Okay.
Yeah. And I think, that has to do with this order n to the -1/2 asymmetry. Yeah.
Well, it's not just the size of, what I mean by that is, and Li Chang will remember this well because I asked him this question years ago, but there's a kind of a simple heuristic to figure out once you know what the invariant measure is, to compute what the effective coefficient should be in the KPZ equation.
Yes, so those are totally explicit, and they're checked, and they sort of even make sense at the continuum scale, ignoring the particle system. Yeah, I think Li Chang's calculation should hold equally well for longer range jumps as well.
Okay.
So as before with the Bertini-Giacomini result, you can extend this to singular narrow wedge initial conditions, and it doesn't really cause you that much trouble. And as sort of alluded to before, if you assume the maximal jump length of the particle random walk is at most 3, this was proved by Amir Demo and Li Chang several years ago. And I'll explain the utility of this assumption in the context of the proof of this theorem as well. So that's for a system of particles on a domain without boundary. And now I'm going to look at particle dynamics with boundary, which I'll thank Ivan for sort of bringing this problem to my attention, actually.
Before you get there, let me ask one more question. So I just want to clarify. So on the full line, the invariant measure for these particle systems, is it Bernoulli? Is it totally explicit, right? Okay.
Yes, it's Bernoulli and sort of things that you get when you condition on the particle number, stuff like that.
Actually, are you working on the full line or on the periodic?
I'm working on the full line, but the result also applies to periodic. If you want.
Okay. Okay. And I guess when you go to the boundary, things will get a little bit trickier with invariant measures.
Yes, so that's actually an interesting point that I'll sort of talk about towards the end of this talk. But yeah, if you look at a dynamics with boundary, which I'll define on this slide, the invariant measure problem becomes very tricky. So thank you. The model for particle dynamics with boundary is if I take a domain with boundary, on the interior, the particles just do the same thing as they did before. They just perform these random walks with the same sort of coefficients. But there's a sort of situation which happens, which is a particle might try to jump outside of the domain, past the boundary. And then if this happens, you just sort of let the particle jump as far as it can without exiting the domain. So on the interior, you still have these random walk dynamics. And additionally, at the boundary, you have annihilation creation dynamics as well. And the coefficients for annihilation creation are basically the same, except you still have an asymmetry, which is again on the order of n to the minus 1/2. And there's a condition which sort of was coined as Liggett's condition, or some long range variation of Liggett's condition. It was coined in a paper by Ivan and Haoshen, which I'll talk about shortly. And this is just a sort of constraint on the particle random walk coefficients and the annihilation creation coefficient. And for long range variations of these models, Liggett's condition, or the analog of Liggett's condition, is sort of not a very nice thing to write down, so I haven't written it down. But it's totally explicit as a relation between the parameters in the model.
So Liggett's condition, you know, the reason we called it this is because it comes up in some early work of his where he's trying to talk about the ergodicity of ASEP on the line, but he's doing it based on this open ASEP. And I think if I remember right, what it means is that if you impose the condition, then the invariant measure, if you look right at the boundary, just one in from the boundary, it will be the same as, well, okay, actually the invariant measure will be the same as if you start with Bernoulli with that density on the infinite line on the left, and then Bernoulli with the density on the right. Is the same true here, that you can kind of simulate that if you looked at this open boundary condition and you just put Bernoulli with whatever the effective density is, that this is when you enforce Liggett's condition, that what you're saying is the same?
I haven't thought about it. Sort of what I'm concerned about mostly is that the particle random walks are sort of a little interesting, even if you just look at the symmetric component, because sort of if I just look at sort of the random walk that the particles are doing and I eliminate the asymmetry, sort of the uniform measure is not the invariant measure for that random walk, because sort of particles, even at sort of the symmetric component of the random walk, still has some asymmetry towards the boundary. Because, for example, if you're at the site 1, you have a higher rate of jumping to the left by 1 than you do to the right by 1, just because sort of longer range jumps will push you towards 1. So the point being here that
but I think what I'm saying is, imagine that you have an effective density that the reservoir, I guess we're on a half length.
Yeah.
Well, whatever. Maybe we're on a finite interval. So there's an effective density that's being imposed on the left. So you can start Bernoulli on that, and then you don't actually have an interaction with the boundary. You would just have the full system without any of these B plus or B minuses.
Oh, I see what you're saying.
But I guess that's hard to believe that would be true, because you have the freedom of the B plus and B minuses. So it's not like you're just going to fix a single invariant measure, Bernoulli to the left, and forget about them and get the same process. Right? Like you have freedom to choose the B plus and B minuses. It's not like there's only one configuration for a given choice of the symmetric.
Yes.
Okay. So then what I'm saying is probably false. But that's what's special about Liggett's condition in the nearest neighbor case.
Yeah, and what I will comment on is that sort of invariant measures in general for this dynamics of boundary for long range random walks is something that I think is fairly mysterious. Are there any other questions before I go on? Okay, so if I look at a domain with multiple boundaries, for example, a compact interval or asymptotically compact interval, you just impose similar boundary dynamics on every other piece of the boundary. And as before, just for technical convenience, you can just think that all of these coefficients for the boundary dynamics have moments uniformly bounded in the scaling parameter. So that's the dynamics with boundary. And the result is that if I renormalize the interface exactly as before, the theorem is still true, except now everything, including the limiting KPZ equation, lives on a domain with boundary. And it turns out that the corresponding boundary conditions that arise in the large N limit are Robin boundary conditions. And as sort of indicated in the second bullet point here, the Robin boundary parameters associated to limiting boundary conditions are explicit functions of the coefficients corresponding to the boundary dynamics in my microscopic model. And there's a subtlety here. which I'll explain on the next slide, it's just a technical point. It turns out that all Robin boundary parameters are actually achievable through this result. And again, in this first bullet point, you can extend this to narrow wedge initial conditions fairly easily as well. So again, because this is an SPDE seminar, I'll be totally explicit and show you my hand what I mean by solving this KPZ equation with Robin boundary parameters. All I mean is that you again take the Kohl-Hopf solution, or instead of looking at the stochastic heat equation from before, you look at the stochastic heat equation with the same Robin boundary conditions. And in terms of what it means to solve that stochastic heat equation, well, again, the solution of the stochastic heat equation is in the mild sense through a heat kernel expansion. So you just replace the Gaussian heat kernel with the Robin heat kernel, and then regularity estimates for that will give you well-posedness of this Kohl-Hopf solution. So that's just to be totally explicit what I mean by solving this SPDE. And if you assume the model where the particles perform simple random walks, this result was actually proven by Ivan and Hao Shen, and afterwards by Sha-Lin, Perek. And in those papers, the model was known as open ASEP. And there's another approach to this problem, again, where the maximal jump length is 1 through the theory of energy solutions, which I sort of alluded to in this last bullet point. So that's just the introduction to this problem, these results. And this is a good time to ask questions if you have any, because I'm going to spend the majority of the rest of the talk talking about sort of the analysis behind them. Okay. So one reduction I'm going to make is I'm just going to work on the compact torus, or asymptotically compact torus, for technical convenience, though the result does hold for the line if you want it to. And as before with this Bertini-Giacomini paper, the first step is to exponentiate your height function in this fashion. And because we're taking the Kohl-Hopf solution theory, we want to show that as you take n to infinity, this exponential transform converges to the solution of the corresponding stochastic heat equation. And one way to do that is to find some sort of feature of this microscopic exponential transform, which sort of emulates some behavior of the stochastic heat equation. And in this case, what you can do is you can compute the stochastic differential of this exponential transform, which is actually, I should say this, originally an idea due to Gartner. And if you compute this differential, you'll get some approximation to the right-hand side of the stochastic heat equation. So here, Ln is some discrete approximation to the continuum Laplacian, which you can think as the infinitesimal generator, the symmetric component of the random walk that the particles are doing. And this multiplicative psi-n factor is some discrete approximation to the space-time modulus. And at this point, what I'll say is that if you work with a model that has this integrable structure, this would be it. There would be sort of no terms after this. And that's, in this context, what it means to be integrable in some sense. So for example, ASEP would not have any of these terms show up. But we're not working with an integrable model, so we have these error terms. And first, these ... terms are terms that were actually analyzed successfully and quite nicely in that paper of Mir Demo and Li Cheng-Sai. And they do it through hydrodynamic analysis. And it's mostly topological, but you can make it quantitative if you want. And then now I just have to explain what this pink factor is. And it's something which sort of, I gave it maybe an overly fancy name, but I'll explain sort of why it's called this. It's a pseudo-gradient nonlinearity. So explicitly, this nonlinearity G is just this function, where here eta tx will always denote a +1 if there's a particle at time t position. Sorry? Oh, sorry. So eta tx will always denote a +1 if there's a particle at time t in position x. And if there's no particle at time t position x, eta tx will always be -1. And this n doesn't mean raised to the power n, it just means that there's sort of some n dependence in the particle system. And these coefficients Ci, J, K decay very fast as any of the indices get very large. So it's a nonlinear function, of the particle system, which is why I called it a nonlinearity. And now, for now, if you assume that the maximal jump length is at most 3, something that I didn't write explicitly here is that the indices in both sums are bounded above by the maximal jump length. So in particular, if the maximal jump length is at most 3, then there's only at most one term in each sum, which corresponds to I equals 1, j equals 2, and k equals 3. And in that case, this g function really is the honest discrete gradient of some nonlinearity of the particle system. And that sort of miracle of a feature itself renders this g quantity one of these ... terms that was analyzed successfully by Amir Gambo and Mi Chang-Sun.
Initially, there were a quadratic term there, right? And then it was killed by that assumption you mentioned earlier.
Yes. So this magical assumption for the asymmetry coefficients, it shows up by, there's the sort of quadratic term that looks very singular, and it turns out to just be canceled out with this magical assumption. And to the end, so that's if the error term in that assumption is n to the -1. If it's n to the -1/2, the term isn't completely killed, but it basically looks like one of these quantities for a magical reason. So that's the role of that sort of key feature with the lambdas in that assumption. But yes, so there is a term that I did hide here. I should say that this is not supposed to be a complete proof of the theorem. It's just to give you an idea of the analysis behind the theorems, because there are many details that are going to be missing. So if you consider longer range models where the maximal jump length can be bigger than 3, possibly infinite, you can just check that this thing is not actually going to be the gradient of any function of the particle system. But there is one sort of feature which makes this sort of a pseudo-gradient and not a real gradient. And that if I take the expectation with respect to any invariant measure of this quantity, for the particle system of this quantity, I'll get 0. And to be totally explicit, the invariant measures for this particle system are really just uniform measures on all particle configurations of a given particle density. So in words, you can think of Gn thus as a fluctuation with respect to all invariant measures, and that's going to be the key feature which makes this nonlinearity accessible to analysis. Okay, so just to recap, this is the evolution equation for the exponential transform. And if you reinterpret everything in terms of the heat kernel in the mild formulation of this stochastic differential equation, the key quantity that we'll want to analyze is this space-time convolution of the heat kernel corresponding to dt minus ln acting on this nonlinearity, this multiplicative factor. And one simplification I'm going to make is just to eliminate the exponential transform inside, just for technical reasons, one being that to analyze this quantity, I'm going to rely on the regularity of the heat kernel. And if I left in the exponential transform, I would have to rely on the regularity of that, which is still at the level of Holder regularity, but it's certainly not as nice because of this stochastic term in the evolution equation. And the other one is that I'm going to compute a first moment of phi, and I don't want to sort of have to worry about the correlations between the nonlinearity and the exponential transform. But of course, you can't just do this because then you're just completely changing the problem. It turns out that to justify this reduction, you need to perform some multi-scale variation of the analysis that I'm going to talk about anyway. So that's just one simplification. And the key starting point, which there's sort of a schematic here, is to introduce an average in the time direction. So what I'm going to do is I'm going to replace phi by psi n, which is the same thing, except I've replaced g by its dynamical average on a time scale of tau being 1/n. So here the schematic is just I'm replacing the value of g by its average on some block of time tau. And this reduction you can sort of justify pretty easily by using regularity estimates for the heat kernel. So now the analysis of this quantity is going to basically consist of 2 steps. One, the first being just sort of computing with respect to the invariant measure. And to this end, it turns out that this key feature of being a fluctuation with respect to every invariant measure of the particle system allows us to apply something called the Kipnis-Varadon inequality from stochastic homogenization which basically states that this quantity, this dynamical quantity, without the tau inverse, is a Brownian motion of timescale n squared tau. And n squared tau being because I've accelerated the particle system by n squared. So this upper bound just follows from a sort of a time average of a Brownian motion, if you want, of time squared n squared tau. And from this, you can deduce sort of fairly straightforwardly an upper bound for this whole dynamic or whole space-time convolution, which means that you'll succeed in showing that this quantity is negligible as n goes to infinity if tau is much bigger than 1 over n. And that sort of contradicts with what I said on the previous slide of tau being on the scale of 1 over n. It turns out that if you introduce an additional average in the spatial direction as well, you can pick up an n to the minus epsilon factor everywhere, and then take tau to be 1 over n to win.
Kevin, just to clarify,
Yeah.
You said Kipnis variant implies that this quantity is Brownian motion, or
so what it basically tells you is that at the level of second moments, you have a CLT for this quantity. Because the particle dynamic is sort of moving so fast, it's sort of mixing very quickly. And this quantity is basically like a mean zero quantity because it's a fluctuation. So the idea is you basically have a CLT for this integral, if you think of the integrals as sum.
But if we're a quadratic quantity, we know that the limit of the quadratic fluctuation does not converge to a Brownian motion.
What do you mean by quadratic quantity?
So if I were to just consider 2 copies of eta, and you know, do a similar time average, that thing supposed to represent this limit of this nonlinear term of KPZ equation.
Yes.
And we know that that guy is not Gaussian.
You're saying that the time average of this quadratic is non-Gaussian.
Just because,
Yeah. So, okay. So what I should say, and thank you for this, is not an actual convergence to a Brownian motion, but what you get is an estimate on the scale of a Brownian motion.
Right. So it scales like Brownian motion.
Yes, is precisely what I want to say. Yeah, thank you for that. And there's another feature here. You need a spectral gap, it turns out, for the particle system, but that's sort of a more technical point. So now that's the expectation with respect to the invariant measure, but we're going to be generically concerned with the expectation in non-equilibrium. And to this end, it turns out that for large-scale interacting particle systems, the model is so complicated that we can't really compute anything explicitly, generically. So what I'm going to try to do is I'm going to try to reduce this calculation to a calculation with respect to the invariant measure, which we know how to handle from the previous slide. And here, there's another reduction I'm going to make. I'm just going to assume that this heat kernel is the uniform measure on the torus, and I'm just removing the short time singularity in the heat kernel by doing this. Again, if you want to justify this reduction, you need some multi-scale variation of the analysis I'm going to talk about in the next few slides anyway. So the first step is to take the expectation of the first moment of this upsilon quantity. And the first step to doing that is this idea from this paper by Guo, Papanicolaou, and Varadon on hydrodynamic limits. So I have it written out explicitly here, but if I take the first moment of this upsilon quantity and I pull the expectation through this integral and this sum, what I'm really doing is I'm taking an expectation of this dynamical quantity with respect to the path space measure induced by the global particle dynamic on the time scale tau, with an initial condition that's basically the particle system around the point y and the time s. And then I'm taking an average over all space-time points, s and y. And that's exactly what's written here. So this expectation of upsilon is bounded above by this double expectation, where here the inner expectation is an expectation with respect to the path space measure induced by the global dynamic with an initial configuration eta 0 that's then being sampled with respect to mu t n bar. The mu t n bar is just, I take the particle system around point S, time S and point Y, and then I average over all space-time points S and Y. So this is sort of the prelude to what's called the 1 block and 2 blocks estimates in hydrodynamic theory. And this is just sort of an elementary calculation, though it's certainly not obvious. So there's a graphic here at the bottom I'll describe shortly. This is the double expectation that I want to sort of show is negligible as n goes to infinity. And what I'm going to do is I'm going to sort of localize this inner expectation, which is really sort of the part where this approach differs from the theory of energy solutions, which is sort of a global approach. So what I'm going to do is I'm going to replace this inner expectation with an expectation with respect to the path space measure, which is defined by the interacting particle system, but if I sort of restrict it to a neighborhood lambda and equip it with periodic boundary conditions, where lambda is basically an interval whose size is determined by how far a particle will propagate in time tau. And really what this replacement is saying is my quantity G is some functional that only depends on a uniformly bounded number of sites, which means if I look at the dynamic on a neighborhood lambda, the statistics of G won't really depend on whatever boundary conditions I put on lambda. And that's just because any information that's sort of created or a discrepancy that's created at the boundary of lambda will propagate into G, the support of G, with small probability. So this is just sort of a coupling argument. You can think of it as a speed of propagation estimate if you want. But now, why does that help us? The point is that this inner expectation is really just a local statistic because it only depends on the particle's configuration on some local neighborhood lambda. And there's a permeating philosophy in the theory of large-scale interacting particle systems, which is that at the correct space-time scales, you don't achieve global equilibrium, but you still achieve local equilibrium very quickly because the particles are sort of mixing very quickly. Since I've scaled the system by a factor of n squared in time, which means that we have a hope of reducing our calculation with respect to the invariant measure, since all we really need to know is that the law or the space-time average law of the particle system is close to the invariant measure, but only when you look at statistics on the neighborhood lambda. So one way to make that sort of precise is by implementing something called the entropy inequality, which gives us this upper bound for the double expectation for any positive kappa. And here ENT is the relative entropy of the spacetime average law UTN bar with respect to the invariant measure. And you can think of this as just sort of the connection between large deviations theory and the relative entropy if you want. So we just have to estimate these two quantities. Turns out for the first quantity, if I choose kappa to be n to the minus 1/2, because the quantity in the exponential is uniformly bounded, elementary calculations will basically reduce the estimation of E1 to the problem at the invariant measure that we had before, which provides us this familiar upper bound. For the second point, for the second quantity E2, it turns out that convexity of the Dirichlet form and the log Sobolev inequality give us this upper bound. So this is something that sort of you can find in the text of Kipnis and Landin, where here UT tilde is the time average law, not the space-time average law, and then classical entropy production estimates, which you can also find in the text of Kipnis and Landin, give an upper bound of this quantity, for this quantity of 1 over n. Point being that E2 is sort of a quantity you can estimate sort of directly with classical techniques. And if you recall what kappa and lambda are, you get this upper bound for E2, which might worry you a little because there's no choice of tau that's going to make both upper bounds go to 0 simultaneously. But if I additionally average in the spatial direction, I can also pick up an n in the minus epsilon factor everywhere, which means I can win if tau is 1 over n. So the whole point here in non-equilibrium is to reduce the calculation by localizing our analysis of the particle system sufficiently, and then just work at the invariant measure. Are there any questions about that? those are a lot of details, but hopefully the idea of sort of reducing to the invariant measure by localizing sufficiently is clear through this strategy. Okay, and in terms of the dynamics with boundary, I'll go over this sort of relatively quickly, and not try to, while trying to not rush through anything really. Basically, you take the same approach, you exponentiate and compute the stochastic differential, and you get the same thing, except there's an additional error term supported at the boundary, which vanishes in expectation with respect to the product Bernoulli measure of parameter 1/2. And there's also sort of a discrepancy in this L tilde operator, which is still some sort of approximation to the continuum Laplacian. But really what I want to talk about is the analysis of this nonlinearity, G. And in particular, as Ivan mentioned earlier in the talk, if you try to apply the same approach, you might run into an obstruction, which is that we have no understanding what the invariant measures of the boundary dynamic are, except if you're in the case of nearest neighbor or simple random walks for the particles. And even that is sort of a delicate problem. So for example, if you tried to approach this problem with a theory of energy solutions, you would run into an immediate obstruction that I personally don't know how to overcome, really what step one would be. Anyway, if you try to do this local dynamical approach, the solution to overcoming this obstruction is realizing that it's not an obstruction to begin with. And the reason why that's true is because if you follow the same strategy, you'll get this double expectation that you'll need to bound in non-equilibrium, where the pink expectation is exactly the same quantity as before, as in the previous problem. And the reason why that's true is sort of maybe hopefully aided by this idea or this picture. If I take a point that's sufficiently far from the boundary and I put a neighborhood lambda around it so that this neighborhood doesn't flirt with the boundary of my domain, the periodic dynamics on lambda are going to be totally blind to whether or not your particle system had a domain globally or not. And then the number of sites where you can't fit such a neighborhood lambda around is, you can show directly, is sufficiently small that their contribution as n goes to infinity is negligible. So that's really the upshot of localizing our analysis. So what that means is that we need to get a Dirichlet form estimate with respect to the invariant measure from the previous particle system for the time average of 1/n. But this sounds maybe too good to be true, and that's because it is. You can't get a 1/n estimate, it turns out. You can't get the optimal estimate because the invariant measures of the boundary dynamic are not the invariant measure I'm trying to estimate the Dirichlet form with respect to. And the discrepancy turns out to be the asymmetry in the model. So we get an n to the -1/2 instead, which is the strength of the asymmetry. But this turns out to be more than sufficient if you're willing or happy to adopt more multi-scale analyses. And there are other additional quantities. So it turns out that you can replace this boundary error term by its expectation with respect to local equilibrium through the dynamical approach. And the local equilibrium on sort of sufficiently small timescales is product Bernoulli because the asymmetry is sufficiently weak. So that's just another application of this sort of local time average approach. And all I'll really say for the rest of this talk is that I mentioned a discrepancy or sort of a subtlety about this L tilde operator. It turns out to be not self-adjoint with respect to the uniform measure on the domain for longer range systems. So you can't use spectral theory or Fourier analysis to analyze this heat kernel. But you can implement an approach with Nash inequalities, it turns out, for special Robin boundary parameters. And then you can extend to arbitrary Robin boundary conditions and even get additional regularity estimates for the heat kernel through a perturbative scheme. But what I will emphasize here is that these perturbative schemes don't work unless you have the Nash inequalities, so the a priori estimates from the Nash inequalities. And every time that spectral theory or Fourier analysis is sort of applicable, so is the theory of Nash inequalities. So this is just possibly a more robust approach to heat kernel estimates in this problem. And I promised sort of further applications, which I'll just leave up here, but I figured that this might be an appropriate time to stop the talk. And I'm more than happy to discuss any of these problems if people have questions. But I'll stop the talk here. And special thank you to this sort of list of people who certainly played a helpful role in these results. And this archive reference is just an archive reference for the first result. The second result, as indicated in the year 20 to 21, is certainly very much in draft version right now, but it should be up relatively soon. Thank you.
Let's thank Kevin for this very nice talk. Other questions from the audience?
Kevin, can you, I'm wondering if you simply forget about half-cool and maybe even do this on torus, can your method apply to get tightness result of long-range exclusion?
So if you try to sort of do a microscopic regularity structures type result approach, or
might not even be like that. If you look at energy solution, one thing that they managed to do is to use Kipnis variant to control this quadratic term at equilibrium. So I'm just wondering, now you have it out of a stationary tool. Can you use it to get some sort of bound on that quantity?
So not for the asymmetry on the scale that you would get the KPZ equation. So that's related to this problem. On the scale where you would get Edwards-Wilkinson or additive stochastic heat equation fluctuations, it does work. It turns out if you just try to sort of, so what happens in the energy solution theory is that you need really global control of the invariant measure. So really what I'm saying is that I'm trying to time average on a local scale, on a sort of mesoscopic scale in this problem. Mm-hmm. And the reason why that's sort of sufficient is because there's a certain expansion that the energy solution theory gives sort of works on. And the more terms you want to get in that expansion, the more you need to time average, the more you need to sort of exploit the ergodicity of the particle system. It turns out that for these quantities that vanish in expectation with respect to all the invariant measures, the additional sort of all but the first quantities sort of vanish, it turns out. So I only really need to access the first quantity, which means that local time averaging should be enough. But if you want to sort of do the energy solution theory thing, this wouldn't be enough.
Can you remind me why do you have to restrict yourself to a smaller time window?
Yes. So that's a great question. So it's the point is here. The larger I want to time average, mm-hmm. sort of the more I need to be able to control the law of the particle system in some space-time average sense with respect to the invariant measure. So if I take a larger time average, my statistic is going to sort of depend on a larger and larger domain.
Right.
But I sort of can't guarantee that on a larger and larger domain, the particle system is still close to the invariant measure. So I need to be sort of sufficiently close to equilibrium to run this strategy, but I don't know that I'm sort of close to equilibrium when the sort of domain that I need to be close to equilibrium on gets larger and larger.
But if I start initial data from something that is not that close to equilibrium, but mm-hmm. close to equilibrium enough for you, then this whole thing would go through.
Yes, and then you need to find sort of what it means to be sufficiently close to equilibrium in this case.
But I assume that would still be better than being absolutely continuous in the limit as it goes to infinity.
Maybe. So this is something that I've sort of played around with a little, but I can't remember if anything sort of looks too promising. But I okay. Agree. Yeah. Does that answer your question?
Yeah.
Okay, are there other questions? Maybe I have one. So mm-hmm. I think at the beginning you have several moment estimates on the jump distributions. So my first question is, do you really need bounded moments for all P, or do you just need it for some large P?
P equals 4, maybe 4 plus epsilon is certainly enough here.
Good enough. All right.
You definitely need P equals 2, otherwise the Laplacian
Sure,
in the equation might be a fractional thing.
Yeah, so that leads to my second question. So have you considered a case where you have P smaller than 2, so you get some fractional Laplacian?
I have, and I quickly realized sort of an issue. The Cole-Hop transform, I think in principle, maybe shouldn't work because the sort of duality between the two equations relies heavily on the chain rule, the Laplacian, which you just don't have for a fractional Laplacian. Exactly.
Sure, yeah.
Does that answer your question?
Yes, but I think I remember that, you know, people like Milton Harari, they have considered these fractional type KPC equations, but I'm not so familiar with them. Have you seen their work on this kind of topics?
Yeah. So yes. So the upshot there is that they don't use the Cole-Hop transform, so they don't need the chain rule. It's just sort of it's just an artifact of the approach. But what they do is they sort of find a microscopic version of the KPZ equation itself, or rather its sort of distributional derivative, and they just sort of work at that level. And they need to be at the invariant measure because they need to somehow make sense of this singular nonlinearity in the equation.
Okay, thank you. Are there further questions? Okay, if not, let's thank Kevin again for this very nice talk. So we will meet again in 2 weeks where we will have Hubert Lacroix and Clément Cosco speaking. Okay, thanks everybody. I stop the recording now.